just past the Agulhas Bank region in the South Atlantic Ocean. They're often thought of as black holes because they rotate and they bring things into the center. But I'll show later they're actually quite leaky. They can leak quite a lot of water out of them. So an outstanding problem in mathematical oceanography is how do we best identify these features, whether it be from observations or ocean model output. So that leads us to data. There's two sorts of data, or two main types of data. There's Eulerian data and Lagrangian data. So Eulerian data describes data in a fixed frame. Examples being on the left, satellite data, or satellite altimetry data, moored buoys, and high frequency radar. And Lagrangian data describes measurements obtained in a frame of reference moving with the flow. So examples are surface drifters and Argo floats. Surface drifters are drifters that are stuck to the surface of the ocean. So they're buoyant and stay at the surface of the ocean, and they go with the water. So they'll travel all around the world. And Argo floats are sort of machines that drop down to a specified depth or a specified pressure, and they follow the flow at that depth. And then every 10 days, I think they pop up, they send out all their information to a satellite, and then they go back down and follow the flow for another 10 days. Each of these instruments measure different things. So satellites can measure sea surface height, sea surface temperatures, ocean color, that sort of stuff. And in terms of getting a velocity field from that, we have to look at geostrophic velocities, but I'll talk a little bit about that later. Moored buoys and surface drifters and floats, they all can measure their velocities, as well as things like salinity, temperature, and some different nutrient levels, that sort of thing. What I haven't touched on here, which I will touch on later, is the use of supercomputers for ocean models. So instead of using real life data, what we can use are really high resolution ocean models that solve the Navier-Stokes equations, which simulate the real world fluid flows. And we can use those ocean models to sort of make sense of what's going on in the real world. So in our approach, eddies are these moving objects, and so we don't really want to see them in a fixed frame. We want to move with them. So arguably the best data for us to use would be the Lagrangian data. That leads me to sort of the underlying mathematics that we need to use in order to identify these eddies. There's a whole range of different methods or techniques, but the technique that I use is developed by my supervisor, and it uses the theory of finite time coherent sets. So imagine that we have this two-dimensional set on the left. You could think of it as a region of fluid. And under three different potential outcomes, we could have set A, set B, or set C. So think of the set on the left. After a finite period of time, it turns into either A, B, or C. Under the dynamics of A, we can see that the boundary length of the set compared to the volume within the set remains roughly the same. But if we look at both B and C, the boundary length increases quite significantly. So I know what I didn't mention here is that the volume or the area of the set remains the same. So the only thing changing from the left-hand side to the right-hand side is that the boundary length is changing. So what we can do is we can define finite time coherent sets as regions of fluid that have a minimal boundary length to volume, or sorry, a minimal average boundary length to volume. So we wouldn't consider B or C to be finite time coherent sets because on average, their boundary length is rather large compared to the volume, whereas the dynamics under A remain quite small. So we would consider the dynamics of A to have a finite time coherent set, but B and C wouldn't be the case. So the way to think about that is finite time coherent sets are regions of phase space or fluid that minimally mix over a finite period of time. And what I mean by minimally mixing is that mixing can really only occur on the boundary of these sets. So if you have this region of fluid surrounded by a region of fluid with different properties, the only way that these two regions can mix is through the boundary. And we can see that if we increase the boundary, we'd have more mixing. So the way to think about these finite time coherent sets is that it's a sort of region that will minimally mix with the surrounding flow. In the ocean, we have eddies, which are the spinning vortices, and they often contain waters of different properties. And one way we define them is that they're regions that minimally mix with the outside area. So this is where we can sort of make the parallel between eddies being finite time coherent sets. And so by definition, we're calling eddies finite time coherent sets. Okay, so when we come into the mathematics, this is where I've taken out a whole bunch of slides on defining a whole bunch of different things because it'll get rather technical. But it's important to mention that what we're essentially doing is we're taking a domain, which we'll call our manifold M, and we're trying to split that manifold up. And what we're trying to do is trying to find a boundary or a codimension 1 manifold, so a manifold of dimension 1 less than the actual manifold. So in this case, think of a line that splits our boundary such that the length of that cut is minimized, divided by the volume is minimized. So for example, we'll have two different boundary conditions. I'm trying to make this as least confusing as possible. We have a region M and we want to cut it in such a way that over the dynamics, or pushing it through the dynamics, on average, the length of that evolving boundary divided by either of the volumes that we cut by is minimized. In a case of Dirichlet boundary conditions, we can't have that gamma intersecting the boundary. So Neumann boundary conditions are really useful when we're trying to find jets or fronts or currents, the boundaries, because we can take a domain and we can sort of just find the line or the curve that splits the domain where the jet or the front is. Whereas you have to go further along to find eddies. Dirichlet boundary conditions, if we take, skip the slide, if we take a region of fluid and we have a rotating vortex in the middle, we know that the boundary that we're searching for can't intersect the boundary of our domain. And so we're essentially searching for a boundary within our domain. Hopefully that made sense, but I can discuss that a little later as well, because I realize now there are a few slides that are sort of essential to make sense for this. How this actually works, or how we can actually compute this, is through an operator called the dynamic Laplace operator, or the dynamic Laplacian. So you might know of the Laplace operator, which sort of gives us information about how heat can transfer through a given domain. Well, the eigenfunctions of that operator tells us how heat can transfer through a domain. And so the idea here is we sort of have an evolving domain. And so we're looking for regions where the heat sort of remains in the same spot. And so that can, well, that's one way of thinking about how from the Laplace operator to a dynamic Laplace operator, you can think of regions that don't mix well. So the heat transfers means that you have mixing. And if the heat doesn't transfer, then you don't have as much mixing. So to link it back to finite time coherent sets, you can consider them as level sets of eigenfunctions of this Laplace operator. It's very high level at the moment. You might not really understand what I'm talking about, but once I get into some of the images later, hopefully it makes a little bit more sense. In mathematical terms, this operator is a self-adjoint elliptic differential operator, which means, well, that finite element methods are probably the best choice to numerically compute them. So, well, I'll talk about how we can actually numerically compute them. So this is just a visual method. Normally I write down all the equations and whatnot, but what we have is we start off with a set of trajectories. So on the top, I've got a whole bunch of different squiggles, and I'll zoom in so you can get a better sense of what these are. So each color, each little curve represents a single particle. So think of a water parcel in the ocean through time. And all we need for our method is all of these different trajectories at different time points. And what we do is we take at each time point the positions of those trajectories and we triangulate them. So these are three different time steps for triangulations, and basically we're connecting the closest particles together. Then what we do is we build some matrices, a stiffness matrix which encodes neighborhood information about the particles with respect to the equations that form the dynamic Laplace operator, and a mass matrix, which is sort of like a normalization matrix. From there, we compute an eigenproblem and solve for the leading eigenvectors and eigenvalues. So what we can see here is, in a global sense, this is just an example, the second eigenvector highlights the Southern Ocean, and in fact that's, I think, the Ross Gyre or the Weddell Gyre. I always mix the two up. And then similarly, we have the South Pacific Gyre popping up in the eigenvector 5, as well as that Ross or Weddell Gyre. And we can see eigenvector 10 also has a gyre in the bottom. But these eigenvectors don't spit out the eddies or the gyres or the fronts directly. What we need to do is we need to perform some sort of clustering algorithm. You may have heard of k-means clustering or fuzzy C clustering. But what we use is what's known as a sparse eigenbasis approximation, which sort of looks to find the sets, well, the most coherent areas, and sort of make everything else non-coherent. So it sort of shows everything else as zeros and the coherent areas as ones. And you can sort of think of these as probabilities of being in a coherent set. So we've got the South Atlantic gyre here and the Ross or Weddell gyres here. And then as an example, I should probably zoom in a little bit. We've got the North Pacific gyre, the South Pacific gyre, North Atlantic gyre with the cut of the Gulf Stream and so forth. So just as an overview, all we need are trajectory information. We don't need any information about velocity fields or sea surface heights or anything like that. We just need the trajectories. And from that, we can find our, in this example, gyres. But what I'll be showing soon are eddies. Okay. So this, what I showed just here is in terms of the ocean. on our Earth, which is a sphere. So there's that one of the issues is distance and area on a sphere are different to distance and area in latitude and longitude coordinates. So what I'm going to talk about now are just a number of different problems you can face when trying to compute these objects when we're on a sphere. But you could think of them in other contexts as well. So rather than just our ocean, it could be the atmosphere of Jupiter or the seas of, I think, Neptune. I could be wrong. So the four main things I'll discuss in this section are what Lagrangian data should we use, what sort of coordinate system should we use, how do we deal with coastlines, boundaries, and islands. So I'll just scroll back up. You might see in here in the triangulations, the continents are missing, whereas when we build the triangulations, you don't account for that just yet. And then lastly, how do we define boundary conditions for our Dirichlet boundary problem? Because it's not so obvious when we are discretizing a continuous space, what the boundary actually is. So the first problem is the data problem. What sort of data should we use? So we could use observed data, whether that be Argo floats, so the floats that drift at a set depth and then come back up every 10 days. The issue with those and drifters, so drifters being the surface drifters, the issue with those are that they're sort of quasi-Lagrangian. They don't follow the true flow of the ocean because they have mass. So they sort of follow and then get deflected because they have some sort of momentum or inertia. So they don't follow the true flow. So if we were to try and understand the sort of birth, traveling and decay of an eddy, they would introduce a number of different problems or errors to our analysis. Another thing we could use is satellite altimetry data. So satellites get the sea surface heights, and then I call this a derived Eulerian set of data. From those sea surface heights, we can compute what are known as geostrophic velocities, and then from those velocities, we could advect virtual particles, and so we have trajectories based on real life data. But the issue with satellites are that they're not super high resolution in the sense that clouds affect their performance. They're not hourly or daily. They're more what is it? I think weekly because of the trajectory of the satellite around the world. So we could use those, and in fact, quite a lot of papers do use those. But we want to understand eddies at a really high resolution. So what we use is model data. So we use 0.1 degree ocean model data from COSIMA, which is the Consortium of Ocean and Sea Ice Modeling Australia. I think that's it. That's out of, I think, ANU, and they run really high resolution ocean models. And from there, we can take the velocity data and we can advect a whole bunch of virtual surface particles and use those to understand what's happening in the ocean. So another issue is that the world's not flat. In the blue lines, I've drawn the straight line between, say, New York and London, or Lima and Sydney, or Johannesburg and Sydney. But the red curves represent the shortest distance between each of these areas. So when we think of distance in latitude and longitude coordinates in, say, an equirectangular projection, they don't preserve the true distance between points. And so we need to think of a better way of computing those distances. We can use the Havesine function and still stay in this sort of domain. But then we have to think about area as well. So because distance isn't preserved, it's distorted, area is also distorted. So on the left, each of these red either circles or ovals or even rectangles represent the exact same amount of area. So you can see a small circle in the equator is equivalent to a large oval in the high latitudes or the low latitudes. And it's actually because the lowest point on this projection is a single point on the sphere. We have this giant rectangle as the same area. So on the right, you can see if we use an orthographic projection, those areas all are equivalent. So we need to think of a way of being able to triangulate all of our points so that the areas of those triangles and the distances of the edges of those triangles are not distorted. One way we can do that is we can take our latitude and longitude grid and we can project all of those points onto the unit sphere. And in that way, all of the distances in three-dimensional space are approximately the same as the distances if you were to take the distance from point to point through over the circle, so that the greater circle distance, it's approximate to the distance between the points in three-dimensional space. And what we can do, so before we were computing a triangulation in 2 dimensions, now we compute a triangulation in 3 dimensions. That then adds a new issue of triangles being computed through the sphere. So what we do is we compute what's known as an alpha complex. So essentially we take our triangulation and we look for circles that contain our triangles that are of a maximum size. So we don't want really large triangles because they'd be the triangles that go through the surface of the sphere. We just want the smaller triangles, which are the triangles we'd expect to be connected. So for an example, in 2-dimensional pictures, because it's quite hard to show in a presentation, the 3D images, we can remove those large triangles using an alpha shape. But the point of this particular slide is the issue of land mass and islands and other boundaries. So when we compute our triangulations on, say, 2D space or on the surface of the sphere, what we'll have is a number of particles in different oceans connecting through continents. Because we don't have any information about continents in our domain, when you just build a Delaunay triangulation, it will connect all those different points. So there's 2 ways that we can remove triangles that cover continents. One way is, again, using an alpha shape, so removing those triangles that are large because they're the circle that encompasses them has a large radius. But the issue with that is if we have very small islands, they'll still remain covered, or if we set our threshold too low, we'll have a lot of disconnections in the center of our ocean. So the idea that we came up with is seeding a number of sort of static particles along the coastlines of each continent. And so we can then remove any triangle that's connected by 3 coastline nodes, and then those triangles are removed and you're left with only triangles that connect ocean particles. And so anything that goes over land is removed. And then the last problem that I discussed that I mentioned was trying to define the boundary of our Dirichlet problem. So I'll go back to the picture here. So Dirichlet boundary conditions are really useful for trying to find eddies. And so we need to make sure that the line that we're trying, or the curve that we're trying to find, doesn't intersect the boundary of that region. But when we have a finite amount of data, we don't have the full continuous field. It's really hard to determine what is the boundary of our domain. So there's two ways that we can do it. We can use an alpha shape again and use any node that shows up on an edge that only shows up once. So we have a full triangulation and any edge in a triangulation that's shared by two triangles would be an edge within the domain, and then any edge that only shows up in one triangle would have to be by definition on the outside of the domain. So we can define the particles by that sort of boundary. Another thing that we can do, which is what I've used in my examples, is we can seed additional particles outside our domain of interest, build our triangulations, and then we're no longer restricted by the alpha choice that we use when we're building our alpha shapes. So that sort of choice of the radius of the circle fitting our triangles. So for an example, on the left is defining a boundary with an alpha shape. And if we zoom in on a certain section, we can see that there's this region of our domain that's connected up by a number of triangles. I'll zoom in by a number of triangles, and those triangles still fit within our alpha shape choice, but we can see that there's just this large gap that really we should be removing so that we can find a better boundary. If we include a whole number of particles outside of our domain when we build our triangulation, we can see that we have a much finer boundary. So this forces all of our disconnecting sets to be in the internal of our domain rather than potentially including areas like this. Hopefully that makes sense. Okay, so that's a bit in the numerical implementation and some of the problems we can face. So now I'll show a example problem. So this is the South Atlantic Ocean. On the bottom right, you can see South Africa. And what I've done here is I've ejected about 1.2 million particles, and I've colored them by their starting longitude. So they're colored from left to right by where they begin. And then keeping that color, I just push them forward through time, and you can see where they end up. What you can see are these number of a few different rotating vortices. Might be a little quick, so I'll slow it down if I can figure out how. Somehow, playback, speed slower. Okay, so you can see these rotating vortices, hopefully, and I'll also pause it, that have picked up fluid from the left and are sort of transporting it, well, from the right and transporting it towards the left. These would be candidates to look at as Agulhas rings or eddies. Everything else is sort of mixing and don't really look like eddies, but these swirls are the sorts of things that we're trying to identify and trying to understand how they evolve. So you might maybe choose one to watch. I might choose, say, this one. So it'll start somewhere on the right and just watch it evolve through time. So maybe take this one. It starts off with light orange colors, but then it starts to pick up other materials. So it gets a bit of this green and light yellow, and as it comes across, it takes on a little of the darker red, and now it's starting to pick up more of that green and yellow. So a lot of people thought these eddies are black holes, that they're only made up of a certain material and they move through the ocean and they dissipate, but they never release material and take in new material to sort of keep its shape. They thought that they have one set of material and it just sort of decays away, never picking up new material. So what we can see here is that that's not really the case. It certainly spits out old material and picks up new material. And so what we want to do is understand how that happens. So what we can do is we can use a different method just to get an idea of what's going on. Or well, I'll show you a different method to get an idea of what's going on. So what this is a plot of what's known as the Okubo-Weiss parameter through, I think, how many days? 650 days, I think. The Okubo-Weiss parameter is what a lot of oceanographers use to define the boundaries of eddies. And what it is a measure of the relative importance of deformation and rotation from a velocity field. So negative values show that rotation is important, and positive values, so the blue here, would represent deformation being important. So in this case, negative values, the red areas, are what a lot of oceanographers would define as eddies. It's probably now the second most used method after using sea surface height anomalies to define the boundaries of eddies, but it's a very quick and easy way to get an idea of do eddies exist, because we are looking for these rotating features. The issue is that the material that these Okubo-Weiss eddies have in them changes. So it's not a method that is mass preserving. It doesn't preserve the material within the eddy. So what I've done in this video is I'm showing 4 different Okubo-Weiss eddies. I've initialized particles within the eddy, and then I just push those particles forward through time. And what you can see, maybe it would be helpful if I slow this one down as well. So speed, slower. Okay, so we have magenta, cyan, black, and green. And you can see that the cyan eddy, the particles in the cyan eddy move westward and then get entrained by that cyan eddy, that magenta eddy. Similarly, the black particles get entrained by the cyan eddy, and the green particles get entrained by the black eddy. So a lot of people used to think that these eddies were, again, black holes, and so you wouldn't have this inter-eddy transport. But what we're seeing is material from an eddy more eastward, so a newer eddy in this case, is getting entrained and transported by an older eddy, which is more westward, which is something that hasn't really been thought about or even observed until now. So this is sort of something new that we've found. So what we want to do is sort of understand each of these eddies independently, but also as a sort of a train of eddies. So I think my title's Agulhas Rings, a relay race. So the way we can think of this is a relay race where each eddy is passing a baton of material to the eddy in front of it and transporting that through.
Michael, can I just ask a question?
Yes.
Is this sort of technology then used for things like oil spills?
Yes.
To track where they're likely to go? Right, okay.
Yeah. Yeah. So an example of where this method has been used or could be used is in the Gulf Stream. When there was the big oil spill with BP, they've done a number of different studies funded by BP. So I think it was a requirement of them with the United States EPA to throw out a whole bunch of drifters so that they could understand the dynamics of the Gulf region. And yeah, definitely oil spills are one of the applications to understand how they move and transport.
Thank you.
And possibly trying to locate the wreckage of a Malaysian Airline 370 that disappeared. Was that used in that too?
Yep. So these techniques on specifically eddies aren't, but the Lagrangian techniques are. So this this whole particle advection idea definitely played a role in the MH370 wreckage to understand where it could end up. So they placed a whole bunch of virtual particles on a map and used the sea surface height satellite altimetry data to create velocities and push those particles forward through time so that they could predict areas where that plane wreckage could be. Another example is there was a certain type of kelp found in Antarctica, on the coastline of Antarctica, which oceanographers were very confused how it got there, because it only exists on a certain island in, I think it's the South Atlantic. So they modeled backwards how it could have gotten there, and they found that they use these sorts of techniques to do that. But back to the eddies, what we really want to understand is how these eddies transport mass, not just on their own, but as a sort of a train or a team in a relay race. So what we do, one other thing I've forgotten to mention is that our finite time coherent sets are coherent sets for only a finite period of time. So the material within them for that finite time remains the same, but we can think of these eddies, because they sort of leak and take new material. We can think of overlapping windows of finite time coherent sets to look at what material changes throughout the eddy. So what we need to do is we need to define windows for all of our different eddies. So if we take a finite time of 90 days, you can ask me later why I chose 90 days, and I'll go into a description about how we had to think about a whole other problem. But we take a window of 90 days as our finite time period, and we look at our Akubo Weiss eddies being stuck within boxes. So at the first day for the first window, one of the eddies is at the bottom right of a box, and by the last day it's still in that box. And essentially we want to take any particle that we have that goes throughout that box as part of our domain. And what we're going to do is we're going to do that for different windows. So we have a window defined for the 1st to the 90th time step, a window from say the 30th to the 120th time step, so a shifted window, and a window from the 60th to the 150th time step. So these are 3 overlapping windows where we're going to look at the eddy, we're going to compute our finite time coherent sets, and look at sort of what material has changed and what new material is in the eddy. So the first thing we need to do, if we think about the method again, is we need to compute the triangulations, compute our stiffness and mass matrices, and then solve an eigenproblem. For those familiar with eigenproblems, we get a whole number of eigenvectors, and then we can visualize those eigenvectors by coloring the particles by their eigenvector value. So we can see that the first eigenvector for the first window shows that this region of the fluid, the dark red region, minimally mixes with the blue region. The second eigenvector shows that this region on the left, this dark red region, minimally mixes with this dark blue region. And this red region, in fact, is part of an eddy. And then the third eigenvector shows this small red region on the left, which isn't an eddy, minimally mixes with the dark blue region in the middle, which is sort of a mix of 2 eddies. And we can see that between Windows 0, Windows 30, and Windows 60, similar features are being picked out. Not exactly the same, but similar features. So that we can see, for example, the third eigenvector for Windows 0 is similar to the second eigenvector of Windows 30, which is in a way similar to the second eigenvector of Windows 60, because they're showing similar regions that are minimally mixing. I haven't shown here how we've computed the similarity, but we use correlations weighted by a mass matrix. So now I'm going to, because I couldn't get the 3 videos to work together, I'm going to show the 3 videos that I had in the presentation I presented before, and I'm going to show it relatively slowly. What I'm going to show are the eddies that we've identified for each of these windows through time. And what you'll notice once it gets to that point, here we are. What you'll notice is that when we compute the eddies for the first 90 days, they remain relatively coherent, whereas the later windows aren't coherent until their time period begins. So you can see now for the first window, those eddies are starting to filament and break up, whereas in the Windows 30, they look quite coherent. And now in Windows 60, they are quite coherent, whereas the first and 30th window are starting to filament quite a bit. So they all represent the same eddy, just at different time points. Maybe I'll speed it up just a little bit more because I played a few times. And now you can see well outside of those ranges. So the first window was days 0 to 90. The 30th window was days 30 to 120. And the 60th window was days 60 to 150. Now at the much later time steps, those eddies defined by these material eddies have broken up. So you can see by day 70, they're starting to filament, but the 30th window looks good. Now the 60th window looks good. They're all the same eddy, but they're defined on different time periods. So the way you can think about this is the eddy for the first 90 days might contain the material in the first video at the top. From days 30 to 120, it might contain material from the middle plot. And in the last video, it might contain from day 60 to 150 material in that video. And so what we want to do is essentially have a window for every day and compute in that center time the material in the eddy. And so you can look at the new material that comes in and the old material that goes out. That's the sort of way we want to look at these eddies. And then what we can do is understand the material that started in the left eddy. Does any of it move into the second eddy or the third eddy or the fourth eddy? And the opposite as well. Does any material from the fourth eddy enter the third eddy, the second eddy, or the first eddy? That's essentially what we're trying to look at. So on that note, that's pretty much all I've got to talk about. There's a couple different references if you're interested in specifically the mathematics underlying those finite time coherent sets. There's a paper on dynamic isoperimetry and the geometry of Lagrangian coherent structures. I like that paper. There's a paper on the method that we use, so the finite element method, to compute these sorts of things. And then I touched very briefly on what clustering algorithm we used. It's called the sparse eigenbasis approximation, and there's also a paper on that. So with that, yeah, I'm open to questions. I'm open to talking about what I'm working on next. Yeah, feel free to ask away. Hopefully you learned a little bit about ocean eddies, and that I didn't skip too much maths for it to not make sense. So thank you.
Thank you so much, Michael. Peter Day has made a comment. These systems seem to be chaotic and probably constantly changing. I assume the maths can get very complicated.
Yep. So in the underlying theory of all of this, so I'm using the application of the ocean, which is a chaotic or turbulent system. And Lagrangian coherent structures is a very big field in dynamical systems that looks at the structure in turbulence. So when you look at a turbulent field and you watch it long enough, you might find structures in that turbulence. And essentially all I'm trying to do is find these structures in the turbulence. So back in this video, we can see that it's quite a turbulent flow, but we can still see these structures emerge. So the maths does get complicated, but numerically we can just apply a method and use our bounds on those applications to make sense of it all.
How do ocean systems like El Nino, La Nina, Indian Ocean Dipole, and the South Annular Mode interfere?
So in the South Atlantic Ocean, I'm not sure they have an impact. But if we were to think about something like the East Australian Current, which would be impacted by SAM or El Nino or La Nina, they could affect the strength of the currents, which would then affect the size of the eddies. So they won't interfere with our method, but they could have an impact on the actual dynamics of the eddy, in which case our method would pick up on those changes. So I'm not sure specifically, but they definitely would have some sort of impact or interference.
Michael, I've got a question about eddies versus gyres. I must admit, I thought they were pretty much the same thing. Can you talk a little bit about that?
Yeah. So eddies are what we think of as a much smaller scale in terms of their spatial size, as well as their lifetime. So eddies typically, we think of two types, mesoscale and submesoscale. So submesoscale are anywhere from a couple of meters to maybe 10 kilometers in size, and they last from, the meter ones last for seconds, but the 10-kilometer size ones can last for a couple of days, maybe a couple of weeks. And then mesoscale ones are eddies anywhere up to say 500 or 600 kilometers. And they last, so for example, these Agulhas rings, they last anywhere from a year to 2 years. But they definitely do die. They decay and then they no longer exist. So we can see them form, travel, and then decay. With the gyres, and I've got a video I can show on gyres, just bear with me. They are much larger in scale, and in fact, I question whether they are even a finite time phenomenon. They could just be a ever-existing phenomenon based on the bathymetry of the ocean. So they might never die. A good example of whether a good example of that sort of question is the Great Red Spot on Jupiter. Would you consider that an eddy or a gyre or just a rotating vortex? Because we've known about the Great Red Spot for near on 400 years now. And the question is that ever going to decay, or is that just a feature that will remain forever? So eddies definitely decay within a time scale of up to say 2 years, whereas the gyres have been around for decades. But to show you a quick video, I think this is the one I want to show. So these are ocean gyres. This is over a 5-year time period. So our eddies would have definitely decayed by now, but our much larger scale gyres remain coherent for the entire 5 years. So the eddies that we were looking at before were in this small region of the South Atlantic Ocean. Let me play that again. They were in that small region of the South Atlantic Ocean. They were much smaller in spatial scale, and they decayed fairly quickly. So if I showed a video of 5 years, they would have disappeared less than halfway through the video. Whereas these large scale features, you can see that there's very minimal mixing between these gyres and the dark blue particles outside of the gyres. These things remain really, really coherent for a really long time period. But you could actually just consider gyres as very long, large eddies. Yeah.
This is getting away from the topic. Sorry, Michael.
That's all right. That's all right. Are there any other questions?
Eliza was asking about tracking pollution or feeding grounds for marine life, and how is the matter in eddies identified?
Yep, so eddies, upwelling eddies take nutrients from the bottom of the ocean, and they suck them up towards the surface. And so a lot of marine life are attracted to these eddies. The way the nutrients, or the way the properties of the eddies are measured in the real world, are by surface drifters and Argo floats. So, so those, where are we? These sorts of instruments can measure all sorts of things like temperature, salinity, chlorophyll, other nutrients. And so the way we can understand what material is in the eddy is by looking at the data from these sorts of instruments if they pass through the eddy. There's been a number of studies on plastic pollution. So there's a scientist called Eric Van Sebille. I'll just try and get the plastic. Here we are. So these sorts of techniques can be used to track pollution. So, for example, I placed a whole bunch of rubber ducks in the North Atlantic. We can see how those rubber ducks sort of get distributed after 5 years. And so these sorts of techniques are used to track that sort of pollution as well. I think I missed part of the question though.
No, I think that covers it. Thank you.
Yep, so pollution and marine life. Yeah.
Okay, thank you. And the next question is, are eddies formed by Coriolis coupling?
I'm not sure what Coriolis coupling is. The Agulhas ring eddies, at least, they form where the Agulhas current, so there's a current that feeds down the east coast of Africa called the Agulhas current. It retroflects, so it turns back in on itself at the base of South Africa. And then you've got the Southern Ocean, you've got the Antarctic circumpolar current that moves from west to east. And so where that retroflexion meets the Antarctic circumpolar current, it pinches off and eddies are formed. So I think I've got a small sort of video of that. Well, actually, I can show it from the Ocean Speed video. Make this a little larger. So, and I'll pause here. So we've got this current that comes down the east coast of Africa, so the western boundary of the Indian Ocean, and it comes down all the way to the base, and then it retroflects on itself, so it turns back. And then we've got a major current that goes around Antarctica called the Antarctic Circumpolar Current. And so if I play this slowly, you'll see the sort of rings form where that those currents sort of meet. It pinches off and the eddies are formed there. A similar thing happens in the East Australian Current. So the East Australian Current comes down the East Australian coast, so the western boundary of the Pacific Ocean, and it turns back on itself and forms these rings. So these are the eddies formed by pinching of the East Australian Current. A similar thing happens in the Gulf of Mexico. So you've got the Gulf Stream that comes up through the Gulf of Mexico and then up the east coast of America, and it also pinches off, forming eddies in the Gulf region. And these are eddies that have been studied quite a lot due to the oil spill, and so these ones are considered to be more of a black hole than the eddies in the open ocean, because they're much less affected by things that can cause mixing, like winds and bathymetry. Hopefully that answers that question.
Thank you. How does the HF radar work to monitor the current tracking?
Yep. So where are we? Here we are. So there's a number of different radar stations along the coast of, say, Australia, and I don't really know how radar works, but my understanding of it, my simplistic understanding of it, is that it sends out a wave and then picks up the wave bounce back. And what it does is, as the currents move, the wave that bounces back has a different property than the wave that it's sent, and so it can measure the velocity that way. So I think if you look at, for example, the Bureau of Meteorology radar, it's a sort of similar thing, but instead of looking at, say, clouds, it looks at surface currents. So I'm trying to get a picture of. No, I got to radar website, but that's not what I'm looking for. But it essentially looks at how the ocean surface is moving, and then it computes the change in difference as the velocity. And it's high frequency, so it's very, it computes those distances over shorter time periods to get a more accurate idea of what the current velocity is, rather than a long time averaged velocity. Hopefully that makes sense. Let me know if that doesn't make sense and I can give you a better answer, but hopefully I got the answer for you.
I think that's fine, thank you. And our last question, I think, is do earthquakes and subsequent tsunamis change anything or just run through?
So earthquakes and tsunamis would have an impact on, they'll definitely have an impact on surface velocities. When waves start to break, but tsunamis themselves don't transport material from where they begin all the way to the end. It's only once the wave breaks, so they really only transfer energy. So they shouldn't really impact the eddies unless the eddies were close to the coastline. They'll definitely sort of have a little wiggle in the velocity field, but I don't think they'll actually move an eddy off course or have an impact on the actual formation or travel or decay of an eddy. So I don't think they'll have an impact.
Okay, thank you. Has anybody else got any other questions or comments? No, I think you've done a wonderful job, Michael. So thank you so much for making a very complicated topic seem relatively clear to us all, I think. So thank you.
I think it was still a little complicated.
Yes, I think so.
Thank you, Michael.
So
Very much.
thank you so much. That's been wonderful. Thank you for your time and your expertise, and yes, that's been
And your
terrific.
patience, thank you.
Thank you.
Thank you.
No
very
worries.
much.
And
Thank you for coming.
this is our last emerging science session for the year. So thank you everybody for your support. And unfortunately, I don't think this session will be running again next year, but I'll certainly advertise it if we do. So thank you again to Michael, and thank you everybody.
Thank you.
Thank you,
Sue.
Thank you,
Sue.
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 And
Thank you.
Cool.